Hello, folks. Professor Fiore back for more op-amp fun. All right, most of the time when we look at op-amps, we talk about a split power supply, a dual polarity power supply, plus and minus 12, plus and minus 15, something like that. What if you're in a position where you can only use a single power supply? That's all you have available, right? I've got, plus 20 or plus 30 or something like that. Is there a way I can use my op-amp? Well, yeah. If you couldn't, I wouldn't be doing this video. Duh. Okay, so let's take a look at one possibility over here. Now, what I have is a little BiFET op amp, pretty standard in 081. A couple of feedback resistors, some new stuff, right? I've got some resistors out here in the front, some caps, my load resistor, my generator, and I've got a single power supply. The trick here is you have to fool the op amp into sort of not quite understanding where ground is. You're going to sort of shift your ground reference. You cannot just hook up a positive power supply and then ground the negative power supply. What'll end up happening is you'll have an amplifier that acts as a half-wave rectifier, basically. So you have to bias the input. Now, you can't sort of just put in half the voltage. Notice here I've got 24 volts. So this would be equivalent, by the way, to a plus and minus 12. All right. I've got a 1K, a 100K for R1 and a 100K for R2. So this should give me 12 volts right at this point, right? This will divide out evenly. The bias resistance looking into this input pin is high enough to ignore. So there you go, 12, 12. This is kind of what you would do in a bipolar circuit, right? Or a JFET circuit, a discrete amplifier. The problem is, if I just stop there, the amplifier will multiply that as part of the input. Because remember, op amps go down to DC. So any DC input will get multiplied up as well. Well, that's fine if you have a buffer with a gain of 1, but what if I have something else? Like in this case, my RF and my RI, 12K over 500 plus 1, that's going to give me a gain of 25. So whatever the DC input is, it gets multiplied by 25 at the output, which clearly would make this thing go into saturation. So not so good, right? And by the way, we also need caps at the output and the input because I don't want this DC value to upset the generator or the load, or for that matter, these things to upset the bias, which it could. So, you might think in terms of adjusting these two resistors so that you have a really small DC value here, and then when it gets multiplied by the gain, you'd end up with, a decent value, a mid value out here. But that's kind of clunky. It also would wind up negatively impacting your input impedance because the input impedance here is going to be R1 in parallel with R2, just like a voltage divider biased bipolar transistor, right? The Z in this circuit is basically going to be 50K, 100 in parallel with 100. So what we need to do is make the gain go to 1 for DC and then be whatever we want it for AC. And the easy way to do that, thinking of the equation, right, RF over RI plus 1, you have the plus 1. So you either make RF go to 0 or you make RI go to infinity for DC. The obvious way to do that is to put a cap in series with RI. So at DC, this opens up. We have a gain of 1. So what should happen is we'll have 12 volts here, 12 volts here for DC. Then the AC input comes in, my 1 kilohertz that I have. That gets multiplied by my gain of 25, right? So I got 100 millivolts peak. I should see 2.5 volts peak sitting out here at my load. Out here, it'll be riding on the 12 volts, but out here, the output cap blocks that. Now, these caps all create lower critical frequencies, lead networks. So you have to calculate to make sure that the critical frequency is not interfering with your desired signal. Basically, you're going to use 1 over 2 pi RC to find that frequency, or you're going to set the frequency and solve to find C more typically as a design. But basically, C out is going to react with our load for the most part. The C in is most likely going to react with the parallel combination of R1 and R2, unless you have a very high source impedance. But typically, it's just going to be this pair. And then, again, similarly, CF will react with RI, and that will set the third critical frequency. Right? So we would set those things all lower than our desired intelligence frequency, so to speak, and whoop, off we go. All right, so let's see what we get here. We can do a real quick DC analysis. All right, so I'll just do a table of values. We don't need the currents. So, you know, if I look at like VDiv, we've said that should be 12 volts. V out of op amp at pin 6 of the op amp, that should be 12 volts. The pin 2 of the op amp, which is actually node 6 here, that should also be about 12 volts, you know, to keep the negative feedback going properly. And if I look over here, sure enough, that's what I'm seeing, right? There's V out op amp is 12 volts. The pin 6 is 12 volts. Okay. VDiv is 12 volts. This all looks fine. All right, so we really are getting that DC gain of unity. Now let's go do a transient analysis here. So I've got a 10 millisecond. We're going to see several cycles of my 1 kilohertz. And again, 100 millivolts, gain of 25. We should be looking at about 2.5 volts out there for signal. And let me put in the legend over here. So here up at top, right, this is V out of the op amp, and that is our desired signal riding on the DC, right? So there's 10, 11, there's 12 volts, there's our DC value, right? VDiv back here, this is this olive color, right? That's the input signal, our small input signal, and you can, if you look close, you can see that's in phase like it should be, all right? And then finally we come down here, here's the actual load voltage, okay, V load, and we were expecting 2.5 volts, right? So there's 1, 2.5 peak. Beautiful. All right. Everything's fine. Love it. Now, fun stuff. What happens if the single DC source you have is kind of noisy? It's not the greatest thing in the world. Maybe it's got some ripple in it. All right. So I've simulated that by simply throwing in a sine wave source, 120 hertz, to represent the ripple. It's not perfectly sinusoidal, but close enough for our work. And I put in a fairly large value here, 2 volts peak, just so that we can see what's going on. All right. Now that signal is going to be presented to the input of the op amp. Okay, it's going to come down through here. There is going to be some attenuation because for the AC, for this 120 hertz, the question is what's X sub C, and then our gen, that's going to be in parallel with R2. So that creates a little bit of a divider, but that residual that's over here is going to get multiplied by the gain of 25 and then go to the output. Oops, I don't want that to happen, right? You know, you don't want the noisy ripple here to become part of your output signal. Let's take a look at what happens. I'll do another transient analysis here. I've upped this to 20 milliseconds because I want to see a couple of cycles of the ripple. I'm not really loving this. So let's take a look at the output of the load here. Here's my V load. And you can see, right, you know, I had that nice signal before, and now it's bopping up and down. That's my ripple stuff, right? If I go back to the original, you know, nice and constant. And this guy, so that signal's coming in and it's messing with stuff, right? So again, if this was an audio kind of amplifier, 120 hertz is clearly audible, it's going to become part of your output signal. You're going to hear that really bad hum. Don't like it. So how do we solve this? Obvious solution is start with a better power supply. That's not always possible. You might have a cheap wall wart kind of a power supply here. Is there something that we can do on the input end to decouple this? And the answer is yeah. If you've looked at the bipolar, the discrete semiconductor videos, then you know there is a way to do this. So here's what I've done. I'll do that again, right? So you can take a look. Here's the original. All this stuff is going to stay the same. But right here, I've added this R3, okay, this 100K, and this bypass cap. So basically, here's what happens. This point is going to be a really good AC ground because of this bypass capacitor. So that is going to prevent almost all of the V ripple from getting into pin 3 of the op amp, right? Before, it just came right down to here. Again, there was some loss because of, a divider basically between this and this, but you were still getting a sizable amount of it, getting multiplied by the gain, and off you go. Here, this is going to be a really good ground, so almost all the ripple is going to drop out here. You're not really going to get anything. And what does come in, you still have this 100K out here, which will create a little bit of a divider with these other things. Remember, you're going to use superposition, so this becomes a short, basically. But in any case, this R3 now represents the input impedance to the amplifier, because this is basically, your AC ground. It's sort of a virtual ground in a way. Right? It's not a perfect ground. It's not a ground. A ground is a ground is a ground, Shakespeare. But close enough. So that'll set that up. If everything works out right, because everything out here is the same, we should see a nice output signal with minimal amount of ripple in it. So again, I'll go back into the transient. Oh, look at that. It's almost like I planned it ahead of time, right? So this is what we started with. You can see the 120 hertz in there. Come over here, boom, nice, right? Doesn't take much, one resistor, one capacitor, and you're good to go, right? So if you're ever faced with this and you can't just get, a higher quality power supply for some reason, because again, it's a lot easier to fix a problem before it's a problem. If you can't do that, then this is a possibility. Or maybe you've made something that's, battery powered and people might use a wall wart on it, but you don't know what the quality is. So to kind of get a step ahead of the user, you can do something like this to guarantee that you're going to get a good quality, even if the user puts in a substandard, if you will, power supply. All right. Okay. See you next time. Have a good one. Take care.